Okay, so we've talked about acid chlorides. Now we're on to anhydrides. Anhydrides, as we just talked about, are a very versatile carboxylic acid derivative. We can make a lot of other ones directly from them. And as far as their reactivity compared to the other carboxylic acid derivatives, they're the second most reactive derivative. So, like we said, acid chlorides are the most reactive. You can make all of them. Anhydrides, you should be able to make all carboxylic acid derivatives from them except for the acid chloride, because then we would be stepping up in energy level. All right, so how does this work? How do we form these carboxylic acids from this anhydride? This water molecule could either add, this is the electrophile, right? We have a partial positive here, but we also have a partial positive here. Is there going to be any preference for which electrophile is greater here, or are they equal? Yeah, they're equal, right? They have the same groups, they have the same electronics all around them. So this nucleophile, this partially negative nucleophile, is going to be attracted to both sides of that equally. And it doesn't really matter at this point because they are identical. So the water molecule would add there. We would form our tetrahedral intermediate that we're so commonly used to at this point. And at this point, we actually have a really acidic species in this, this oxygen down here. Essentially, it's like a hydronium ion, but it's actually even more reactive, more acidic than a hydronium ion. Why is that? Well, hydronium ion is H3O+. This is similar to that, but we essentially have H3O+ attached to a big electron withdrawing group. So this oxygen is positively charged, but all of these oxygens are also pulling electron density away from it, making it even more positive, more acidic, more reactive. So how can this tetrahedral intermediate react with what else is around it to make it more stable? Well, we have lots of water in solution still. So what's going to happen is we're going to transfer a proton to a water molecule. And this will be a slightly favored equilibrium because the hydronium ion will be a little bit less reactive than this species here. So that would produce our tetrahedral intermediate, again, that can now collapse back down. And I'll also write the H3O+ here that we just formed. And essentially at this point, when this collapses down, it's going to kick out the best leaving group. At this point, if it were to collapse down, it probably would have kicked out this as the best leaving group. This hydronium ion is very acidic. It's the best leaving group. But the thing that would be most stable here by itself, we have to either kick out CH3-, we know that's not very good, OH-, also not very good, or this carboxylate. So the carboxylate we know is the most stable of those three options by itself because of the delocalization of that O-. So that produces the acetic acid molecule from this side, and then this side would give us the carboxylate. Essentially, that carboxylate is not going to be around very long because it's going to be very much attracted to this strong acid's proton. We have a big partial positive right there. So a final proton transfer will bring us to our 1-2 molecules of acetic acid. So that's what's going to happen. That's what we are going to form when we treat an anhydride with water. All right. Okay, so we saw how water reacted with these anhydrides. What about an alcohol or an amine? So take a minute, pause the video, draw what products we would have with each of these, and then come back. Okay, so if we have an alcohol react with this, it can add to either side, and the leaving group would be the carboxylate, right? So one side of this would turn into the carboxylic acid, and the other side would then turn into an ester. Again, we could say that alcohol added to that carbonyl, the electrons kick up, forming that tetrahedral intermediate. We get a proton transfer, they come back down, kick out the carboxylate leaving group, and at that point, a proton transfer would occur to make that carboxylic acid. So some of you might be thinking, well, now we have two separate products. Is that very useful? Are anhydrides that useful if we're making a mixture of products? Well, maybe we really only care about that ester product, and we still have a problem though, right? We have a mixture of things. But why would these be really easy to separate? Yeah, thinking back to chapter 19, we could use an extraction, take advantage of the extra acidity of this carboxylic acid, treat it with a base, such as sodium bicarbonate or just hydroxide itself. That would deprotonate this, sending it to the water layer, while this would be still organic soluble. So these are very easily separated, which makes anhydrides still a very useful tool for organic synthesis. What about amines? Well, amines, again, are going to do the same thing. They're going to add to one side. Doesn't matter. The sides are the same. They're going to kick out a carboxylate. And at that point, we would then have the carboxylate. The amine that added in would ultimately form a species that looked like this. So a little bit of an acidic proton there. This nitrogen is usually pretty okay with a positive charge, but this positive charge also has this inductively withdrawing group because this oxygen is pulling electron density away from it. So why do we need greater than 2 equivalents? Well, another NH3 can come in acting as a base, deprotonate that to form NH4 and the amide. So again, we're going to form a mixture of products here. Again, these are easy to separate. This is charged, this is charged. Throw it into a separatory funnel, mix things up. Those will be in the aqueous layer. If this is more than just a carbon, that would be in the organic layer as it is neutral. So that's how anhydrides can react. What about mixed anhydrides? Okay, so here we have a mixed anhydride. What does that mean? Back to our nomenclature, it was mixed because this side of the anhydride is different than that side. Are these useful? Well, let's take a minute and you pause the video and put in all the products that you would see in this reaction and then come back. Great, you already did that. So why aren't they useful? Well, the alcohol can again add to either side of that anhydride. Both sides are reasonably similar sterically. This chain is going to be kind of pushed far away from this other stuff because that's the more stable conformation. So CH3 versus a CH2 with a carbon that's farther away from that electrophilic position is going to be relatively similar in electrophilicity. So essentially this O could add to carbonyl A or carbonyl B. If it adds to A, what is it going to make? If it adds to B, what is it going to make? Hopefully you already have those drawn out. And if you haven't, this is a good time to try and match up what you have drawn out. So if you added it to A, that would form the ester that looks like that plus acetic acid. If you added it to B, that would form this carboxylic acid plus the ester on the other side. So in this case, we do have multiple products where we would really want just the product that we were desiring. We organic chemists want to make things in high yields. Maybe we wanted this molecule here. Well, we don't have it in a good yield because a lot of it's making that instead. So that is why they are not useful. Because mixed anhydride is useful? No, they make product mixtures, which is not ideal. Okay, moving on.